Hi everybody, we're in the last module here, starting with Relativity of Chapter 33, where we will be going over modern physics now. So relativity, I'm sure you guys have heard it at some point. It's the big Einstein theory that everyone loves to talk about and is in every space sci-fi movie ever. What you may not know is he didn't actually get the Nobel Prize for relativity. Anyone know? That's right, it was the photoelectric effect, which we covered couple sections ago, maybe even last chapter. So that was as a fun fact. We can see here for relativity, general relativity, you can see, right, everyone's seen the mass warping the space-time around it. So, fun picture for a fun topic. Let's get started. So if we come over here, for concept 1, 19th century understandings of physics led to quandaries that Einstein resolved with his theory of relativity. So what people were seeing is, at the time, their only tool belt had Newtonian physics, which was F equals ma, and they said that describes the motion of things under a force field, right? But they slowly saw that they could only calculate so precisely when things would happen in space. So orbits of planets were always a little bit off. Um, some other things that they were observing were also not quite right. So they thought, hey, we need a better system to describe the motion of these larger, massive bodies. Newtonian physics was breaking. So then for concept 2, the principle of special relativity underlies all of special relativity's starting implications. Okay, so what this confusing statement is trying to say is that special relativity's core concept was that whatever reference frame or whatever motion that you're trying to describe, the physics of that motion doesn't break. So physics will still apply regardless how fast you're going, how slow you're going, or with regards to any other point in space. And so we can see that then in concept 3, measures of space-time and the simultaneity and order of events depend on one's reference frame. So pretty much how fast you're going will determine how you measure time, space, and even just the order of events like this is saying. So we have a couple of equations to describe this. Should I write them out? Just look at the equation sheet. But pretty much what's happening is you can have length contraction. So if you're in a frame of reference, like this, so you have a stick, you're at rest with respect to the stick, you will see it as a length L. But if the stick is suddenly moving with respect to you, so now you remaining at rest, and now the stick is moving with some speed v, it's going to have a new length, L prime, and it should be shorter. Because as it speeds fast, you try and measure it, it's going to appear shortened in length. And it's only going to be in the direction of motion that's lengthening, contracting. So the width should not change, right? Because it's moving in the x direction, the y dimension will not contract, only the x. Okay. So before I talk about time, let me take a quick step back and just discuss what I mean by a frame of reference. So prepare your minds to be blown a little bit. So right now, I assume you're sitting at a desk or in a chair at least, and you feel like you're not moving, right? You're in a frame of reference that you would say is at rest. But if you were to kind of like zoom back and go to the moon, so you're looking from the moon to the earth, again, you're sitting on the moon now, you feel like you're at rest, but you look back to where you were on the earth, and you would see it moving. So now, what was a non-moving frame of reference on the earth looks like it's moving with respect to the moon. So that's what it means to be in different frames of reference, is that you're just kind of moving around and seeing how things are moving with respect to wherever you are. So that's the easiest way to think about it, is that you're always in the non-moving frame of reference, and everything else is moving around you. And this, of course, is only easy to do in what are called non-inertial frames of reference, so things that are not accelerating. So as long as the room that we're sitting in is not accelerating, we're not going to feel a force pushing us anywhere. So we could be at rest for all we know if we're moving at a constant speed. And so that's where special relativity has that restriction. You have to be in non-inertial frames of reference. The general relativity is where you can move out of that regime. And so now I'll talk about time dilation. So rather than the length contraction, you get time dilation for things moving at different speeds. So if you had a clock on this piece of wood also, it's measuring the time, and you measure the time it takes while it's in a moving frame of reference. The time will move slower. The time will dilate out. So my clock in my frame of reference, right? So over here, we said that V is 0. So our clocks are moving the same. The length of wood is known to be this L. But once it's moving past this at the speed of light, or some fraction of the speed of light generally, then you get a change in the length of the wood, and you get a shortening of the amount of time that you would see on the clock. So that would see here, we would see here for some length of time. Concept number 4, Lorentz transformations can be used to find space and time coordinates of events in different reference frames. So now we can say we have these set of equations, which are the Lorentz transformations, to do this transformation between at rest time and length to in a moving frame of reference. And so you can see that there. I'll go ahead and just pause and write them out so I can refer to them. So now I have the coordinate transformer going from a frame at rest S to our moving frame of reference S prime. Again, coordinates that are not along the axis of motion for our moving frame of reference are unchanged, just like with the piece of wood. If we're moving this way, the length contraction occurs in that direction, not this one. So only the x really changes for that. And then we have our time dilation term, which depends on how far we're moving x. Okay, so the distance does come in to how much time dilation you experience, right? It wouldn't just depend on the time, it would depend on the distance. And you can check here and make sure that the units are correct, right? This should be units of seconds minus seconds, just like this is meters minus meters. Okay. And this gamma term out front is just this funky ratio that has to do with how fast you're moving. Okay. So let's look at this term. Does gamma get bigger or smaller as you go towards the speed of light? As v goes towards c, this approaches 1, which means this gets really, really small, because it's 1 minus something really, really close to 1. And so then this term will get really, really big. So the closer you are to the speed of light, the bigger the change between x and x prime and t prime, which is what we would expect. As you go closer to the speed of light, things get more and more wonky. So now we'll go on to concept 5. A common misconception regarding Einstein's work is that it implies that everything is relative. Not quite, right? So the relativity had to do with the physics being consistent through all these different frames of reference. So that's what we should consider the relativeness, is that the physics stays with them. They don't break the physics as they approach the speed of light. And then for concept 6, there is a special relationship between mass, energy, and momentum and relativity. Well, yes, as you start to change length and time, you're going to have changes to the energy and momentum, right? Because they rely on mass and time to calculate. Okay, and I'm just going to go ahead and pull over the equation sheet and see what we have here. So underneath relativity, we do have, well, I misspelled Lorentz factor and our time dilation. So that's what this gamma term is called, is the Lorentz factor. We have time dilation. Then over here on the top, our length contraction term, velocity. So if you have something that's not at rest and you have another object moving past it, you can see kind of what the total velocity would be in a frame of reference that is at rest. Lorentz transformations, this is going from the rest frame to a moving frame. And then down here we have our energy and momentum terms, along with an invariant space-time interval, which is a little funky. I'm not sure if we really have to worry about it. And for the last concept then, we have relativity connects electricity and magnetism. So there's a really good diagram in the book that I don't know if I can really reproduce too well, but pretty much it's saying that you can either consider two scenarios where either you have a charged rod and a proton, and it will feel an attractive force if they're both at rest to each other, or you can accelerate the rod one way and the particle the other, or just accelerate them together, and you get a current, right? So you get a current in this rod being produced, which produces a magnetic field, and then the proton would then feel an attractive force due to the B field. So that's pretty much how it relates. You can either have just straight up E field force, or you can consider it to be a B field, B cross V force. Okay. With that, that's pretty much it. As usual, please email me if you have questions, and good luck finishing out the semester. Okay, bye.